final lecture of the session. Antonio Peralta from Spain on maps preserving the lambda-Aluthge transforms on products.
Thank you so much. Thank you so much. Can you listen to me?
Yeah.
Okay, I'm sharing. So I hope it is working. So can you see my screen?
Not yet. Oh, now.
Not yet?
Yeah.
Okay, thank you. Well, it's a big pleasure to take part in this non-associative day online. So thank you very much to all of you for spending part of your time listening this presentation. It's a big pleasure to share these moments with you. So special thanks are given to, sorry, I don't know. Is there any problem with the, maybe? Okay, I think it's, okay, special thanks are given to the organizers of this activity because they did a hard work to make this meeting possible, and we all appreciate what they did. Okay, so in principle, I'm talking about preservers of lambda-Aluthge transforms. In general, the second part of the title, I mean, lambda-Aluthge transforms will be just a special case of what we shall try to present during this presentation. And first of all, let me say this is important, that the talk will be mainly introductory, so I will try to skip technical arguments and proofs. Of course, you can imagine that in most of cases, the arguments are quite complicated and probably need a lot of time to see the epsilon delta details, but in general I will try to let you have a general impression of what we are doing, especially from Granada. Well, why are our preservers problems so attractive? At least they are very, very attractive for me, or they have been. In such a way, I developed my part of my research career as researching on studying problems in Jordan structures. Jordan, they are all non-associative. They can be Jordan algebras in functional analysis, of course, but they can also be JV-star triples. You will get an idea of what I'm talking about. But in recent years, maybe during the last 6 or 7 years, I discovered the connections with preservers problems. And the connections are so deep and so exciting for a researcher that you get involved trying to understand this kind of different approaches to different problems. Okay, so I would like to think about preserver problem like a challenge in which you have a fixed structure of relation or product or whatever you prefer, which is being preserved by a mapping which is in general not assumed to be linear, nor continuous, nor any other properties, so nor satisfying any other property. So how can we, I mean, set the typical problem in preservers? This is one way to do that. Suppose you have two mathematical structures, capital A and capital B. These are two mathematical structures like we have here. And suppose that you have, okay, they are mathematical structures, but they are living over linear spaces. So we have addition and scalar multiplications. And suppose you have two products, and well, let me call them products, but they could be just two variables maps on capital A and capital B. They will be in general products, in general, associative or Jordan or quadratic in many different senses. And suppose you have two relations, two partial relations given by these two symbol of symmetry, sim, one of them on capital A and the other one on capital B. And suppose you have in general just a mapping. We are not assuming linearity nor continuity. This is just, well, let me assume that this is a bijection. Capital Phi will be a bijection from the space A onto the space B, but no extra hypothesis on phi is assumed for now. Well, we shall say that our mapping phi preserves the relations sim A and sim B on products whenever it satisfies the following. If any element, any vector A is related to a product of two elements, B and C in A, related by this sim of A relation, then the corresponding images, I mean, phi of A is related to the via the corresponding relation, partial relation on B with the corresponding product of the two images of B and C. So this is the general statement of a mapping preserving relations from A onto B and up to products. We can say up to products. Okay, we shall say that our mapping preserves the relations on products in both directions when here this symbol can be replaced with if and only if. So we have the images are preserved if and only if the original elements are also preserved. So this is in general the definition, and pay attention, we are not assuming any kind of linearity nor continuity. There is another variant of this kind of games. The game is quite simple. Here you have, we have already set the hypothesis. And what is the goal? The goal is quite simple. Suppose you have such a mapping. Can you distinguish or can you find very good products on A and B and very good relations sim A and sim B for which any mapping preserving the relations on products is automatically linear, or moreover, if you are very, very lucky, can you actually determine the precise form of every such a mapping preserving the relations sim A and sim B on products or on both ways? So this is very important. I mean, it's a very attractive thing because in general, we are not assuming the collection of hypotheses on our maps are very, very weak. Okay, there is a variant of this game, which is the following. Suppose that we assume linearity for our map. So T is now a linear bijection from A onto B. And we can say that this linear bijection preserves the relations A and V on general elements. Now we are relaxing that they preserves the relation, that the mapping preserves the relations on products by simply saying that it preserves related elements. And this is in one way. And of course, we also have preservers in both directions. Okay, so this is a typical problem in preservers. There are two, in general, there are two possible variants. For the second one, we allowed the mapping to be linear. And in the original setting, the more general setting, the mapping is not assumed to be linear, but it preserves some relations on products. Okay, how can we find examples of this? Let me take you back to the 80s in the 20th century, and let me rediscover with you two results by two Japanese mathematicians, Yosuke Hakeda, and Kazuyuki Saito. Both of them prove the following. Suppose M, capital M, is a von Neumann algebra. I think most of people in the audience are very familiar with C-star algebras, von Neumann algebras. So M is a von Neumann algebra, or more generally, if you feel more comfortable, an AW star algebra, which is a more general thing, a more general object. We need to admit that capital N admits no abelian direct summands. This is important. So we must exclude the abelian case. And N is just a simple C-star algebra in general. Okay, fix for the corresponding products in the previous problem, fix the associative product in M and also in M. And for the relation, fix the simplest one, which is identity. Two elements A and B are related in any of these algebras, if and only if they are the same element. So this is the most obvious relation, the most obvious possible relation. And fix a mapping, capital Phi, which is assumed to be symmetric. Symmetric is commuting with the corresponding involutions of the C-star algebras in the domain and in the image. This is it's a very natural notion. And we shall also assume that phi preserves equalities on products. This is exactly one of the previous problem for this concrete product, the associative one, and the identity for the partial relation. Then they conclude, I mean, Hakeda, I think this is due to Hakeda, he concluded that such a mapping is always real linear and a star isomorphous. It preserves product and involutions. Okay, involution is nothing exotic because it was part of the hypothesis, but it preserves automatically products, associative products. And the second case, that was the result with Saito, they tried to replace the associative product it was considered in the first case by the natural Jordan product existing in NEC star algebra, which is this one. This is very well known to be one of the most natural examples of Jordan structures, and they still keeping the relation as the identity on both algebras. And then they also conclude that a mapping, just a mapping, preserving, well, a symmetric mapping, this is needed, but the mapping preserves equality on products, must be a real linear, now Jordan star isomorphous. So in other words, you cannot conclude in general that the mapping you are getting is complex linear, but it is real linear, and it preserves associative product or Jordan product, which is the natural setting. Hakeda and Saito actually prove more general conclusions because they tried to analyze what was the minimum requirements to get the conclusion. And they use a kind of, probably you are familiar with this notion, they concluded that actually all you need is a system of n times m matrix units. So what is that? Suppose you have a sister algebra A, admitting a unit element. So we are playing in the unital setting. A system of n times n matrix units is just a collection, finite collection of elements in our sister algebra. All of them denoted, they could form a matrix, if you like, Uij, satisfying the three properties we have on the screen. I mean, I'm not, okay, maybe the last one is that the sum of the elements in the diagonal of this matrix is the unit element in the sister algebra. When you multiply elements in this matrix, you have a rule to compute the corresponding product. This is the standard thing. And when you take the transpose of Uij, what you get is Ugji. So this is the standard notion of a unit matrix when you are actually playing with scalar matrices. And Hakeda actually proved that whenever you have two C-star algebras and the domain is a unital C-star algebra admitting an n times m unit matrix with n at least 2, then any bijection preserving identities on products and also symmetric must be also in this, as we commented before, a real linear star isomorphy. So it preserves, in some way, it preserves associative products. And similarly, if what you have in your hypothesis is a bijection preserving identities on Jordan product, which is this one, and also being symmetric, this is important, what you get is a real linear Jordan star isomorphous. So in both cases, you are starting to feel how the non-associative structures are among parts of the natural problems since the beginning of the theory, because we are in the 80s, we are still being. Now let me play with more general structures. Maybe you are familiar, or someone in the audience is actually familiar with the notion of JB-star triple, maybe not. So I decided to make a very short or brief introduction to JB-star triples. Okay, I chose the title JB-star triples. I apologize with hardest permissions if you allow me to copy hardest book. So in general, you know, probably the easiest way to introduce JB-star triples is is telling you that all C-star algebras and all JB-star algebras, in the sense of Kaplansky, they are all examples of JB-star triples. But as you probably remember very well, the possibility for a C-star algebra to be reflexive reduces to the finite dimensional case. But if I tell you that we can find JB-star infinite dimensional JB-star triples, which are Hilbert spaces, then you get examples of JB-star triples which are not in general C-star algebras. Another way to introduce JB-star triples is the following. It was already pointed out by Poincaré at the beginning of the 20th century that the famous Riemann mapping theorem is no longer valid for complex Banach spaces with dimension at least 2. So you cannot expect to classify all simply connected domains in arbitrary complex Banach spaces. But you know what they can be classified and completely in general complex Banach spaces in a complete way are the so-called bounded symmetric domains. I'm not going to spend a lot of time. Let me simply say that this is a purely holomorphic property, still being a purely holomorphic property, nothing but that. All bounded symmetric domains are in one-to-one correspondence with the open balls, or if with the closed open balls of what we know nowadays as JB star triples, complex JB star triples. That was a very deep result proof by Wilhelm Kaup, a German mathematician, in 1983. And he proved that there is a one-to-one correspondence between bounded symmetric domains in arbitrary complex Banach spaces and the open unit balls of the the elements in the class of JB star triples, complex JB star triples. So we have here we have a picture of Wilhelm Kaup. He is a very well-known mathematician. I mean, unfortunately, he passed away years ago. But anyway, his result is one of the best known results in holomorphic theory in complex Banach spaces. And now we have a motivation to introduce the formal definition of a JB star triple. I assume that most part of the audience, most people in the audience are familiar with C-star algebras, but maybe not with JB star triples. So a JB star triple is just a complex Banach space, maybe use the symbol E to denote it, with a triple product, which is this mapping here, which is bilinear and symmetric in the outer variables. So in X and Y, what we have is a complex bilinear mapping, complex bilinear and symmetric mapping. And in the middle variable in Y, what we have is a conjugate linear mapping. And it satisfies three main actions. The first one is a Jordan identity, which is this one on the screen. I'm not spending too much time on this, but let me simply tell you that it is the obvious generalization of the Jordan identity we have for Jordan algebras. But now in the case of maybe rectangular matrices and maybe other generalization of JB star algebras, spin factors, for example. The second one is a purely topological action, telling us that whenever we fix the first two variables in the triple product, what we get is a Hermitian with operator with non-negative spectrum. So both are, these are, second one, the first action is purely algebraic. The second one mixes algebra and topology. And for the third one, what we have is a generalization of the famous Gelfand-Neymer action for C-star algebras. This is actually an equivalent reformulation of that action in a more general setting. Well, probably you are feeling this as too abstract. So I'm feeling a bit unsure about this definition. Don't worry, don't worry. If you feel more comfortable, let me tell you, let me provide you a few examples to let you feel more comfortable with the definition. For example, every C-star algebra, capital A, is a JB star triple with the original norm, but now replacing the triple product by this one. the one we have on the screen now. I mean, the triple product of x, y, and z will be xy star z plus zy star x over 2. So we need some kind of symmetry on the outer variables in this definition. This is a very natural product. And if you remember the original results by Cadizon in the 50s, when he was studying surjective isometries on C-star algebras, the related product which is preserved by any surjective linear isometry is this triple product, not the associative one. Even the Jordan product is not in general preserved by surjective linear isometries. For example, another example, if instead of having square matrices in the finite dimensional case, you consider rectangular matrices or infinite dimensional rectangular matrices as bounded linear operators between two general complex Hilbert spaces H and K. You cannot in general have a binary product on B of HK, but you can still employ the previous expression to keep the space of all bounded linear operators between two general Hilbert spaces with the structure of JB star triple. And this is the second example we have now. We shall find the same example when we consider the so-called Cartan factors, maybe a few minutes later from now. In particular, every complex Hilbert space is an example of a JB star triple, as I promised before. So the class of JB star triples is strictly wider than the class of C star algebras. And finally, we are in a non-associative algebra day. Let me tell you that every JB star algebra in the sense introduced by Kaplansky in the 70s is actually a JB star triple for the triple product that Kaplansky was already considering in his famous seminar in St. Andrews at the Scotland Mathematical Seminar. So we find concrete examples of JB star triples in most branches of associative C-star algebras and non-associative JB star algebras. Well, another result from the 80s, and now I'm playing with JB star triple theory. This is now a result by my friend and admired colleague Jacob Friedman from the Jerusalem College of Technology, and the previous Japanese mathematician Yasuke Hakeda, who considered the problem, this preserver problems, when you have two JB star triples. In general, suppose you have capital M will be now a JBW star triple. Let me simply say that this is a JB star triple, which is actually a dual Banach space, an extra hypothesis. And we must assume that it does not contain any abelian direct summand. We must exclude abelian summands because they provide counterexample to the conclusions. And M, the second space, is just a general JBW star triple, no restriction on the codomain space. Consider the following operation. Now, instead of having a binary product, they consider this product. P of AB will be the triple product of ABA. If you think a little bit, this is no longer linear on V, it's actually conjugate linear on V, and it is no longer linear on A because it's actually quadratic on A. It's a kind of a strange product, but it is very, very natural. And they still fixing the relation as the identity. And so what they obtain? They obtained the following: any bijection, which is not assumed to be linear nor continuous, nothing, but they assume that this bijection preserves identity on quadratic products of this form, must be automatically a real linear surjective isometry. So it is from my point of view, it is a very deep conclusion, like in the case of the previous results by Hakeda and Saito, because they are obtaining linearity, real linearity for free, just from assumptions, from preservation of certain products. Nothing but that. Now the triple product, if you think a little bit, if you allow me to say that. Here we have a picture of Friedman. I couldn't find pictures of Hakeda and Saito. That was my fault. With Jacob, I have a personal link. So anyway, well, let me try to think a little bit more on the conclusion by this beautiful result by Friedman and Hakeda. By the time that they proved the results, the so-called Van Axton theorem was not properly discovered in the real setting. I mean, what is that theorem? The so-called Van Axton theorem tells you that a linear bijection between two JV-star triples is a triple isomorphism. I mean, it preserves triple products if and only if it is an isometry. So preservation of triple products and preservation of distance is an equivalent property when your spaces are JV-star triples. This is an additional advantage of working in JV-star triple theory. But if you relax complex linearity to real linearity, the conclusion is not always true. I mean, any real linear surjective isometry need not preserves in general triple products. So be careful when you try to apply that for real linear surjective isometries. And let me tell you, by 1988, the description of all real linear surjective isometries between general JV-star triples was a completely open problem by that time. It was later rediscovered that in most of cases, you can actually, from that property, from real linearity, for a real linear surjective isometry, you can actually deduce preservation of triple products in most of cases, but not in general. This is just an historical comment. The result dates back to 2004. It's a much more recent. So by 1988, the conclusion in Friedman and Hakeda theorem is as general as possible as it could be by that time. Okay, and now the other part of the title in my talk. So now lambda-Aluthge transform. If you think a little bit, in all our previous results, we were considering the partial relations as the identity. I mean, two elements A and B were related if and only if they were the same elements. So that was a very, very simple relationship. Now we are trying to replace that simple relationship by something more, I mean, more chaotic. Is the lambda-Aluthge transform. So let me introduce, or let me recall the definition. Suppose you have two von Neumann algebras, M and N, and suppose you have an element, A, in your von Neumann algebra, for which you can always find its polar decomposition. I mean, you can write A as U times the absolute value of A, and this is the polar decomposition of A, meaning that this absolute value is nothing but the square root of the elements of the element A star A, and this partial isometry U is nothing satisfies that this projection U star U is nothing but the range projection of this positive element in your von Neumann algebra. So this is the standard polar decomposition of an element A, of a general element A in any von Neumann algebra capital M. And what is the lambda-Aluthge transform of any such element A? So if you give me any positive lambda between 0 and 1, okay, this lambda is just a real number between 0 and 1 in this interval, we shall define the lambda-Aluthge transform of this element denoted by delta lambda of A to this element. This is going to be the lambda power of the absolute value of A times the partial isometry U times the 1 minus lambda power of the absolute value of A. So in some sense, we are, this is the original polar decomposition of A, in which the whole absolute value is living on the right-hand side of the partial isometry U, And in the lambda-Aluthge transform, we move part of this absolute value from the right to the left. And which part of it? Just the lambda power of it is moved to the left. This is the classical definition. It was introduced by Aluthge in 1990. Probably you know several properties. Here we have a picture of Aluthge. This Aluthge transformation has been deeply studied and applied in different contexts and problems, mainly in operator algebras, but it also admits some interpretation in the Jordan theory, and it is always an useful tool. Why? Why is that useful? Let me just recall several remarkable properties of this transform. Well, when the lambda is zero, I mean the zero Aluthge transform of every element is itself. This is trivial. And let me comment that historically speaking, Aluthge only introduced the 1/2 Aluthge transformation. In general, he only considered in his original work in 1990, lambda equals to 1/2. Well, it's very easy to check that if you have a complex linear or a conjugate linear mapping, which is preserving product and involutions between two von Neumann algebras, then it automatically preserves lambda-Aluthge transforms. So these are the typical examples of mapping preserving Aluthge transforms. And this is true for every lambda in 0, 1. There is a nice property when your original element A is actually a normal element, and this you already know well this definition, it commutes with its transpose, then the lambda-Aluthge transform of it is itself. So for normal elements, the lambda-Aluthge transform makes no changes on the elements. You get the identity on them, on all of them. And actually, there is a related notion, which is able to characterize this lambda-Aluthge transform. Let me recall that an element A in a von Neumann algebra M is called quasi-normal if it commutes with the product of A star A. So this is the definition of a quasi-normal element. And there is a result combining, an old paper by Brown, 1953, with a more recent contribution by Jung Ko Pierce. You can deduce that for any element A in a von Neumann algebra, you can say that A is quasi-normal if and only if the absolute value of A commutes with the partial isometry in its polar decomposition. And that is also equivalent to say that A is a fixed point for a lambda-Aluthge transform with some lambda between 0 and 1. Excluding the identity, which is lambda 0, then this characterizes quasi-normal elements. So it's an extra knowledge on the elements. Well, and now preservers, what could be the maps called preservers of lambda-Aluthge transforms? Now it's going very, very simple. First, let me introduce, if we keep ourselves faithful to the historical development of the theory, we originally find a result concerning linear maps preserving lambda-Aluthge transforms. Suppose you have two von Neumann factors. Now in the hypothesis, the authors, which are Fernanda Botelho, Lajos Molnar, and Jergo Nagy, they only consider von Neumann algebras which are factors. And they fix a real number between 0 and 1. Of course, they exclude the case 0 is because the 0 Aluthge transform is the identity. So there's nothing to preserve there. And they consider, or if you wish, this was already covered by Hakeda and Friedman or Hakeda and Saito theorems. And they consider a linear mapping, a linear bijection between these two von Neumann factors. And they prove that the following conclusions hold. If your domain factor, capital A, is not of type 1, 2, so this is not a 2 by 2 matrices, the space of 2 by 2 complex matrices, Then a mapping preserves λ-Aluthge transforms if and only if there is a star isomorphism between these two factors and a non-zero complex scalar C, for which your mapping is nothing but this C times is a scalar, is a non-zero scalar multiple of a star isomorphism between these two von Neumann factors. It's a very nice result. So in other words, if you prefer here, the relationship, the product is still, they keep the original product, PAV is A times B, the associative product, while the relationship, the partial relationship is being a λ-Aluthge transform of B. So we replace the identity here by this more complex connection between elements. In the case that you have the case of 2 by 2 complex matrices, the description is a bit more complicated. So I'm not stopping on, I'm not spending too much time on the details, but let me say that in any case, all these kind of linear transformations, preserving λ-Aluthge transforms between factors, von Neumann factors, they are well known by Votello, Molnar, and Nagy results in 2016. So we are getting closer and closer to our dates. Here you have pictures of Fernanda, Lajos, and Gergo Nagy. I think it's always nice to see the faces of the original authors. I always like to find them. Well, as you know, nowadays in functional analysis, those people studying preservers will like to relax the actions concerning or the hypothesis concerning linearity. So we all would like to say our mapping is not assumed to be linear. It's not assumed to be continuous. So this was also the case of preservers of λ-Aluthge transforms. But as I mentioned at the beginning of my talk, we need to impose an extra good behavior, maybe on products, maybe on Jordan products, maybe on different types of quadratic products, if you allow me to speak in that sense. So the first conclusion, the first result came 1 year later than the previous result. It is due to Fadil Chababi, who was by that time working in Lille, in France, with Mostafa and Bekta. And he proved the following. Suppose you have two complex Hilbert spaces. You need to assume that H is at least two-dimensional, and you fix lambda between in the open interval 0, 1. I mean, he's also excluding lambda equals to 1, because that was a very, I mean, actually what you get there is the transposition. You are exchanging the roles of the first and second component in the product. Well, a bijective mapping on B of H or from B of H onto B of K preserves λ-Aluthge transforms on products if and only if that mapping is a complex linear or a conjugate linear star isomorphism. So it automatically preserves complex linearity or conjugate linearity and also the associative product. And pay attention, has not assuming that the mapping is symmetric. This is an advantage in this setting. The hypotheses are not including the property that phi is a symmetric mapping. Okay, in our terminology, the product here is the associative product, while the relation between elements is being a λ-Aluthge transform of B, where lambda is, of course, fixed here in the interval 0, 1. Well, as before, we need to connect with Jordan. Sorry, what was the problem? Okay, with Jordan structures, non-associative structure. So if you replace, you could think about replacing the associative product we were employing in the previous theorem by the Jordan, the natural Jordan product. Sorry, sorry for this noise. This was a conclusion. This was a result of Chababi and Mbekta. Mbekta, I think, was the PhD advisor of Chababi in France, and they proved the following: in the similar under similar hypothesis, A mapping, a bijective mapping from B of H onto B of K preserve λ-Aluthge transforms on Jordan products if and only if it is a complex linear or a conjugate linear map preserving associative products and involution. So that this was it was quite a strong conclusion, because now, if you think a little bit, we are replacing the associative product by the Jordan product, but we are getting a very similar conclusion here. Okay, the relation is still being a λ-Aluthge transform of the other element for a lambda fixed between 0 and 1. Here we have pictures of Fadil and Mustafa. There was an open problem when they published this result. What can we say when the natural product here, PAB, is this AB star? So that was open when, I mean, this kind of products were an open challenge when we discovered this contribution. So, of course, if you remember, we had in general avoided commutative factors, and actually we need to avoid the existence of the complex plane as a factor in our structures. The reason is obvious if you think that this sample you have on the screen is a clear counterexample to the conclusions in all the theorems I have presented until now. And now let me present what we did or what we contributed in these lines. Yes, 1 year later, 1 year after that Chababi and Mbekta published the results, we decided to explore the following natural problems. Suppose you have two general for Neumann algebras. So we wanted to replace B of H spaces and for Neumann factors by general for Neumann algebras. And we needed to assume that M contains no abelian summands. This is by obvious counterexamples. And we fix lambda between 0 and 1. And for any bijection, no linearity at all is assumed here. We consider the next properties. The first one is preservation of the λ-Aluthge transforms on products plus being a symmetric mapping. The second one is preservation of the λ-Aluthge transform on Jordan products and also being a symmetric mapping. You can always try to get the combination of two hypotheses in a single statement, which is H3 and H4. In this case, we have preservation of λ-Aluthge transforms on product of the form AB star, or similarly, preservation of λ-Aluthge transform on products of the form A Jordan B star. And these are the natural problem that you can pose in general. So we are relaxing the hypothesis, saying that they are for Neumann factors in Botelho, Molnar, and Nagy theorem, sorry. And we are also considering general von Neumann algebras instead of B of H spaces, as in the results by Mbekta and Chababi. And the goal is clearly, can you conclude that your mapping phi, your bijection phi is additive or moreover linear, in some sense, real linear, conjugate linear? Let me also say that when you are dealing with a factor, if you have a mapping which is real, is highly probable that your mapping is actually complex linear or conjugate linear. So no kind of mixed properties can appear in the setting of a factor. But when you have a general von Neumann algebra, then the conclusion is not always clear. Actually, what you can get is a mixed property of both linearities. Well, let me also say that if you assume H1 or H2 or H3 or H4, the inverse mapping also satisfies the same hypothesis. No, I mean, it's not important. The inverse is a kind of symmetric statement for M and N up to the non-existence of abelian summand in the domain. And second, let me comment that if you solve the problems for H3 and H4, you are actually solving the problem for H1 and H2 in a very general way. So we focus on H3 and H4, at least for this talk. Let me simply comment what we did. So we studied the problem for general von Neumann algebras and bijective, not necessarily linear maps, satisfying the hypothesis for, or we had to focus on the case of B of H spaces because we didn't find any more general result when we are dealing with H3. And what are the conclusions in that setting? If you have two general von Neumann algebras satisfying the hypothesis in H4, so you don't have, you cannot admit commutative factors or commutative summands in M, then a mapping preserving λ-Aluthge transforms on product of the form A Jordan B star satisfies that. It maps the self-adjoint part of the domain for Neumann algebra into or onto the self-adjoint part of the code of the for Neumann algebra in the codomain. And the restriction of this to the self-adjoint part is nothing but a Jordan isomorphism. So this is quite interesting, even from the point of view of physics, because the self-adjoint part of a von Neumann algebra is actually what is interesting for a physicist. Okay, and finally, if you also assume certain complex linearity, you can actually deduce that what you get is a kind of mixed form of a complex linear Jordan star isomorphism. You can decompose your von Neumann algebra in your domain as a direct sum of two von Neumann subalgebras given by a central projection PZ. On one of them, your mapping capital phi is complex linear, and on the other one is conjugate linear. And in both cases, it preserves Jordan products in both directions. So it's the most natural result we could get. But concerning operator spaces, we could actually prove something more general. If you remember my comment before, in general, the results by Mbekta and Chababi are not covered in the case in which the natural product is given by A times B star. But we were able to finish also in that case, and we more or less determine the general structure of any mapping preserving λ-Aluthge transforms on products of the form A times Jordan B star. But I'm not paying too much attention. Do I still having 7 minutes or something like that? Yes. Well, actually I had a battery of partial technical conclusions you can get, but I will skip them in order for the sake of brevity. So I will skip technical details, even if they are stated in a very, very mild statements. So I will skip this part in order to go straight to the final partial relationship between elements, which is the relationships given by being a truncation of. So if you remember in the first results, the relationship between elements was A is related to B if and only if A is equal to B. Later, we replace being equal to by being a λ-Aluthge transform of. And now in the final part of this talk, we shall replace the relationship by being a truncation of. What is a truncation of an element? So let me go back to B of H. And on B of H, I think this is a very old notion. It is deeply studied and used in operator spaces. We say that if you have two operators, A and B in B of H, we say that A is a truncation of B if and only if A star B is equal to A B star A. Okay. This can be, sorry?
No
No,
problem.
no problem. Okay, so this can be rewritten in terms of this triple product. Do you remember the triple product we employed for C star algebras? That was this one. ABC, the triple product of ABC is equal to AB star C plus CB star A over 2. This is 1/2 of this. If you think a little bit, A is a truncation of B if and only if the triple product AAA is equal to the triple product AVA. So actually, this is telling us an important property. Being a truncation of is not a property of operators. Actually, neither it is a property for elements in a C-star algebra. It is actually a property for elements in a general JB star triple because you can employ this as the appropriate definition, and you can actually consider being a truncation of another element in the most general setting of JB star triples in general. So this was the definition we started to study, and we shall say that whenever you have two elements A and V in a general JB star triple capital A, we shall say that A is a truncation of B if and only if the triple product of AAA is equal to the triple product of ABA. So it makes sense, it's a natural concept, and it's an obvious generalization. So, and now this is the game. I'm proposing to replace the partial relationship by the one defined by A is related to B if A is a truncation of B. This will be now the new game. Can you determine the structure of a bijection, not necessarily linear bijection, preserving this relation for on products of operator? We can find a result by 3 Chinese mathematicians. This is quite recent, 2022. Jia, Shi, and Ji, and they prove the following. If you have two complex Hilbert spaces, both of them having, or at least H, having dimension at least 2, and you have a not necessarily linear nor continuous. This is important. We are not assuming continuity for capital Phi. This is just a bijection. Then they prove that phi preserves the truncation of products of operators in both directions. So the product is the associative product while the relationship is being a truncation of. And then they prove that that is the case if and only if your mapping is given by a unitary or an anti-unitary operator U on H. So this is another equivalent version of the famous Wigner's unitary anti-unitary theorem, if you think a little bit. It's nothing but that. It's quite surprising, even from my point of view. Actually, this is done for the associative product and the relation being a truncation of. But now you can also consider this quadratic product, which is the one employed by Friedman and Hakeda in the 80s. And you're still considering the relationship being a truncation of, which makes sense in B of H and also in any JB star triple. And then they prove that you're still being in the same case. I mean, your mapping is given by a unitary or an anti-unitary element. Now transposition is also allowed. I mean, you can switch the order in your variables because it's quite natural for this quadratic product. You can interchange. I mean, this is symmetric in A. It's a symmetrization of a symmetric product on the external variables. So this is always true. I mean, you get the same conclusion up to multiplying by 1 or minus 1. I mean, the real numbers 1 or minus 1. And you get the same characterization of those bijections preserving truncations of on products on these Jordan quadratic products. So in other words, if you prefer, I prefer this point of view. In order to avoid the use of lambda unitaries or anti-unitaries on everything, you can simply say that capital Phi is a real linear triple automorphism on B of H. Nothing but that. You can say in a single phrase all these kind of properties, which is another equivalent reformulation of the celebrated Wigner's theorem for quantum mechanics. And now, just a couple of minutes. Let me simply say that B of H is just a simple example of what we know under the name of complex Cartan factors. There are 6 types of Cartan factors. The first one is the space of B of HK of all bounded linear operators from between 2 Hilbert spaces. You can think about them as rectangular, infinitely rectangular matrices. And we are employing the same triple product we were using for sister algebras. For the type 2 and 3 Cartan factors, we need to define a kind of general transposition on B of H, which is given by a conjugation and the usual involution star. A conjugation is just a conjugate linear isometry of period 2 on your complex Hilbert space. And you can define this transposition, which is a complex linear mapping, which is, reversing the associative product, but it is complex linear, not only conjugate linear. So what you get, you can consider symmetric maps for that transposition, and then you get the notion of Cartan 2, type 2 Cartan factors, or you can consider anti-symmetric operators for that transposition, and what you get are the Cartan factors of type 3. Moreover, you can find the so-called spin factors or the Cartan factors of type 4. These are the spin factors in quantum mechanics in the Lorentz group. Nothing but that. They are all examples of Cartan factors and JB star triples. And there are other types of Cartan factors which are exceptional. They are finite dimensional, but they cannot be represented inside of operator spaces. They were already known in the famous paper by Einstein, Jordan, Wigner, and von Neumann, when they classify the finite dimensional Jordan algebras. These are examples of Jordan algebras which were already appearing in that paper. So they must be considered also for Cartan factors. Let me simply say that, as in the case of C-star algebras, you can embed any C-star algebra inside some B of H. You can actually embed any JB star triple inside an L-infinity sum of Cartan factors. So these are called atomic JBW star triples. This is a result due to Jacob Friedman and Bernie Russo in California. And having all these properties in mind, what you can get is the next very recent conclusion we published in Results in Mathematics 2024. And we prove the following. Suppose you have 2 atomic JBW star triples, capital A and capital B are just 2 atomic JBW star triples, meaning arbitrary L-infinity sums of family of Cartan factors, and you have just a bijection from A onto B. No linearity nor continuity is assumed, but it preserves truncations of triple products in both directions. That is, A is a truncation of the triple product BZV if and only if its image is a truncation of the corresponding images, of the corresponding triple product of the corresponding images. Then we conclude that I forgot. We need an extra hypothesis for the Cartan factors of rank 1. Rank 1 Cartan factors are Hilbert spaces. For Hilbert spaces, continuity is not automatic. We need to assume that our mapping is actually continuous when restricted to rank 1 Cartan factors, Hilbert spaces. Then we prove that actually phi is an isometric real linear triple isomorphism between these 2 atomic JBW star triples. This is also related to Wigner's theorem, but I think my time is almost over. So that was all I had in mind for today. Thank you very much for attending my talk.
Okay. Thank you. Are there any questions? So this was a very broad view of the topic. So let's thank Antonio once more.
Thank you.
And I want to thank the speakers of all this session. the next session, the final session of today, is to start in an hour. So thank you so much.
Thank you so much. Thanks a lot.